So carry on from what we were doing in the last video, which was doing calculations on PV curves and getting into the idea of engine cycles or heat engine cycles and calculating the amount of work being done in the cycles. Here's a classic example of something that you would have seen in a problem with a thermodynamic cycle or a thermal cycle that looks like this. It involves an isothermal process and then an isobaric process and then an isochoric process. And what we can look at is how would I visualize that in terms of a piston? What exactly is happening? So here you'd have isothermal expansion. So obviously heat was put into the piston and then the volume is expanded isothermally. Okay, now interesting thing to note was since it's isothermally, the temperature here at the beginning is equal to the temperature here at the end. So there'd be no change in internal energy over here. And what would then have to happen is the piston would have to reset. So it would have to be cooled. And if it's going to be cooled isobarically, probably what's going to happen is the piston head is going to be pushing down. Okay, and as it's pushing down, it's venting at a source that is maintaining a constant pressure, or it's cooling and being compressed at the same time. So heat energy had to have been removed from the system here. Okay, and we can see that. So the temperature here at that isotherm is 700 Kelvin, but because it's moving to another isotherm that would look like over here, okay, the temperature would drop to 300 Kelvin over here, all right? And then something would happen within the piston, maybe an ignition of fuel or heat being put in, and then all of a sudden it would jump to a higher pressure and a higher internal temperature without doing any work, so there'd be no change in volume. Okay, and then the whole system would cycle up again. Okay, so here we would have work being done. Here, work is going to be going in the other direction. So the work is going to be done on the piston from the outside world. Okay, the pressure times volume, that would be the total amount of work being done from the outside world. And then in order to reset, okay, heat would have to be put in the system to bring it up. Okay, so what kind of questions would arise from that? Okay, well, you could understand that the question could be calculate the total work done in the cycle. In order to calculate the total work, you would have to calculate the area under here. And you do that in a few different steps, okay? So the first step would be to calculate the total work. If I would draw this out, if I calculate the total area under there for that isothermal expansion, I've shown that in a previous example on how to do that. Okay, so that work would be equal to nRT, and then I think it was like ln something over something, right? Let's go see what that was. I think it was like P2 over P1 or V2 over V1. Let's go see it. Let's see if we can find it. Okay, so let's find that isothermal expansion formula. I think here it is. ln V2 over V1, or it would be P1 over P2, I think, or P2 over P1. Okay, so if I go back here, where am I here? Yeah, so we can do V2 over V1, and that would give me the total work done for that first place, okay? And then if the question is really asking what is the actual work being done, it's looking for the area under here, I would have to take that value that I've calculated and subtract it by the amount of work done on the system, which would be this area here, okay, which is pretty easy to calculate. Okay, that area there is going to be a constant pressure times the change in volume is going to be equal to the work done over there, okay? And so in that regard, I would be able to subtract 1 from 2 and calculate the total energy in here. Another question that could be asked is how much heat is put in at that point over there to reset the cycle? Well, the amount of heat that would be put in would have to match the work under that curve. And we can figure that out completely because for that part over here, for that isochoric part, for this part, if I was to look at the first law of thermodynamics, okay, there is going to be a change in internal energy. Okay, so the change in internal energy is equal to the change in Q minus delta W. But because there's no volume change, because there's no volume change, I don't have a change in work. So to solve for Q, how much heat you put in, all I'd have to do is look at the change in internal energy, and then the change in internal energy I could figure out, okay, on its own, I could figure out just from my temperature changes, 300 Kelvin to 700 Kelvin. All right, so then I could do this, for example, 3/2, if it's a monoatomic gas, 3/2 times N, if I know the moles of gas, for example, are, okay, I could calculate the change in internal energy, or I would just have to understand that the heat would have to be equal to the amount of work that I'm putting under that graph. Okay, I'd have to recycle that. Okay, so that's just an example, just to carry on from what we did before. But really what we're going to be after today in this little video is looking at the Carnot cycle, which is an ideal version of an engine that would give us the maximum type of work being done. Okay, and I presented this in the last video where you have adiabatic processes. I have an adiabatic compression over here, an adiabatic expansion, and that system, the Carnot cycle, maximizes the area under this curve, which then gives me the maximum amount of work that I could do in a type of engine without losing energy to the environment, as much energy to the environment. Okay, so just to go over that process again, the Carnot cycle was developed for a heat engine. Okay, the engine isn't going to make work out of nothing. The engine is the work that is being created by an engine is being created by heat flowing into the engine. And what we know from the laws of thermodynamics and just engines in general is that we would never be able to convert all of that heat energy into useful work. A significant portion of it is going to be lost due to cooling, since the fact that I have to cool the piston to come back down to recycle. A significant portion of that energy is going to be lost due to the cold sink, as well as to friction and all these other things. But the adiabatic processes here of the Carnot cycle tries to maximize the efficiency of that engine. And that's what we're going to be after today. Okay, so in this adiabatic compression, I will start to get an isothermal expansion. In order to do an isothermal expansion, heat has to flow into the system, which is causing the system to do work. Okay, and then the momentum of the piston as it's expanding is going to continue to expand without heat flowing in, and that would cause an adiabatic expansion, which changes the internal energy and makes the gas cooler. Okay, and then as the piston starts to contract and compress, heat energy would be removed from the system and cooled so that it would do it isothermally, and then the inertia of the piston coming down is going to cause an adiabatic compression. Okay, along with fueling a little bit of fuel into that, or putting a little bit of gas into that piston again, is going to cause this to jump to another isotherm. Okay, and that's your classic Carnot cycle that maximizes the area under here and the work being done. So how would I calculate the efficiency of that Carnot cycle? Okay, so from the energy and power chapter, we know that the efficiency of any type of heat engine is going to be equal to the work that it did divided by the total energy supplied. And like I said, it would never be 100%, because in order to get that heat to flow through the system, I have to draw it to a cold sink. Okay, the greater the change in temperature, the greater the efficiency of that engine is going to be. You want to drive that heat through the system, and to reset the system, you have to remove heat from the system. Not all of it can go to work. Okay, I have to bring that piston back down, so I got to lose some heat. Okay, so it would never be 100% efficient. Okay, but if I found the work that I did divided by the total heat, that would give me my efficiency. So in a heat engine, you have the hot gases coming in that can be generated by a coal steam generator, and for example, in a steam engine, we make that steam really, really hot. Okay, on the other side of the piston, okay, that hot gas is going to flow into a piston, but on the other side, I have to have a cooling sink. So remember all the power generators that we looked at, nuclear power plants, they all have cooling the greater the difference in that temperature, the greater the efficiency is going to be, the greater the work, the greater the power of that system. Okay, so we always have to have a cooling sink. Okay, and so the energy is going to be flowing through. There'll be a driving force to push that energy through, and some of that energy is going to go into useful work. So the equation here says that from that heat energy, some of it's going to go to work, and some of it is going to go to the cold sink. Okay, and if I rearrange that equation, the total work done is going to be the total amount of heat energy I put in minus the heat that went to the cold sink. Okay, and so the efficiency, as we described above over here, is the total work that's done divided by the total heat that's put in. And then if I substitute this for work, QH minus QC over QH is also efficiency. And if I factor out QH, the equation for efficiency of an ideal engine would be 1 minus the heat lost to the cold sink over the total heat that's put in. Okay, so how can I use that in a problem? Okay, so for example, a car engine has an efficiency of 20% and produces an average of 23,000 joules of mechanical work. How much heat energy is discharged from the engine per second? Okay, this is something that we can use in a practical calculation in our cars if we want to look at how much fuel are we wasting in our cars, how much heat energy are we wasting into the streets of Accra just by driving around. Okay, and you can find that from the efficiency. Most of your engines have an efficiency rating. All right, so if I know my efficiency is 20%, okay, 1 minus QC over QH is 0.2 or 20%. If I rearrange that, 1 minus 0.2 is equal to that ratio, which is equal to 0.8. I'll need that for later on. Okay, and so efficiency is equal to work divided by QH. All right, so 0.8 is equal to 23,000 joules. Okay, that's the useful work that I'm doing divided by the total heat that I'm putting in. If I rearrange that, I can solve for the total heat that went into my engine. And now that I know my total heat, I can go back to this equation up here and solve for the heat that is being dissipated in my cold sink. And that's going to be this. QC is equal to 0.8 times QH. So 80% of the total heat that went into my engine is going to be dissipated. That's 9.2 times 10 to the 4 joules. Okay, and I can imagine if that happens every second, I'd be wasting 9.2 times 10 to, not 10 to the 11, but 10 to the 4. Okay, that didn't turn out. So 10 to the 4 watts. Okay, what is that? That's 92 kilowatts of just wasted energy. Okay, it's a pretty useful calculation. All right, so in our ideal engine, and you're going to be asked, in a Carnot heat engine, calculate the efficiency, and they'll tell you temperatures. Okay, the temperature of the hot sink and the temperature of the cold sink. Under these conditions, calculate the efficiency. Okay, so I can make my engine more efficient by creating a greater temperature change in the engine. Okay, and that kind of tells you if you're in Ghana, we drive our cars and our cooling systems break really, really fast because it's so hot. Or people put in water instead of a coolant into their cooling systems. If that's the case, you can't have a cold sink for the engine. And so you're going to lose efficiency in your engine. So if you want to make your car more fuel efficient, your large Land Rovers or whatever you guys are driving, you really got to spend money and make sure that your cooling system is working perfectly. The radiator fan, the coolant levels. If you want to do that, you can probably pay for the car by the savings that you're going to have in fuel efficiency. Okay, so if you want to make your car efficient, make sure that there's a greater difference between hot and cold. Okay, so the hot temperature of the fire inside the piston minus the cold sink divided by the hot temperature would give me that efficiency. The greater that temperature change, the greater the efficiency. Okay, now no engine is going to be ideal. It's never going to follow this perfectly. This would be a perfect world where everything is reversible in the Carnot cycle, but you're also getting energy loss due to friction and other things like that. So this would be like the ideal efficiency of your engine if it was only that simple. But there's other factors due to friction and making things that are irreversible after they're done. I can't go backwards because I've lost gas or I've lost heat from the system. Okay, and that's it. Okay, the next little video I'm going to make is just about entropy and explaining how entropy can explain why engines go from hot to cold.